Corey, what is the problem? The p function?
P of x equals 11, or x to the 11th.
Sorry, I'm not on here. What's that? He's going to tell me. I just need to get this going. Thank you. Okay.
P of x equals x to the 11th minus 5x to the 4th plus 10x cubed, or yeah, 10x plus 9.
Okay, let's get started.
I've had my hand ready. I forgot that.
That's right.
He's getting better with his hand before he was all over the place.
All right. So this was the task. So let's just quickly recap. What have we done? We started the course by building what? Accumulation from rates. So it was like one side of the story. And then, more recently, we're going the other way, and we're building rate from accumulation with the other side of the story. So by the end of the course, then, we'll see that it's just all one story. Okay, that's our goal. This is all a coherent set of ideas, and there's a grand conclusion at the end. Okay, and that's I think that's a great thing that we're not just looking at a section by section and learning to do different sets of problems, but we're tying this all together. There's somewhere we're heading, okay? And so at the end of the course, we'll see that. So now we're working with, we're getting rate from accumulation, and we're actually going to kind of take an alley journey here, a side road journey, where we're going to learn many rules for finding the closed form rate from accumulation with rules, okay? But just because we're doing that, it doesn't mean that we're just going to turn off our brain to the ideas behind the rules. And we'll see that later today. A new rule we're going to learn is very much about some very important ideas and not just knowing the rule in the end. Okay? So anyway, when we do these, when we're finding these closed form rate functions from accumulation, we're going to start to see that we'll have to combine the rules. We're going to have to use many rules at once. Like, for instance, this example that you had, it actually used all 4 rules in order to do it. And so what will sound like a broken record is the first question we'll always ask with these functions where we're using many rules at once is, first question we'll ask is, what is the overall structure of the function? Because that will govern the overall rule that we'll use, the first rule, right? So that's the question we want to ask here and start getting in the habit of. All right, I need to find the closed form rate function. I need to apply the right rules. So the first question we ask is, what is the overall structure? So which of the 4 rules matches the overall structure of this function p? Is it number 1, number 2, number 3, or number 4? 4. Some people are saying number 4. Do you agree with that? The overall structure of this is? Yeah, it's a sum or difference of many functions. So the first rule that is applied is the one that applies to the big picture of the function, which is a sum function. Okay, so if our p is, say this is g plus h plus j plus k, then what is the rate of change of p with respect to x, right? No matter what notation we use, we practice that. We practice saying that. It's all, whether we use the prime notation or the dx notation or our r function, it's the rate of change of p with respect to x. So what is the rate of change? If these are my four functions that we're adding together, what's the rate of change of p?
The rate of change of g with respect to x.
Okay.
The rate of change of h with respect to
All right, stop right there. He said the rate of change of g with respect to x plus rate of change of x. It's a minus, so we can treat that two ways. We can make that minus, or we can, yeah, we can think of this as plus minus 5. Either way, it's fine. So you want to do minus? That's great. Okay, someone else take over. Plus? No, not j prime of x. How, the rate of change of j with respect to x. Rate of change of k with respect to x. Okay? See how quickly you abandon what we want to do. But yeah, practice always. Practice no matter what the notation is. And all of them are what we call the derivative. Okay, so that's the buzzword. But rather than, so derivative kind of, it's moving away from actually reflecting the meaning. That's why we want to always call it rate of change. So no matter what notation we have for the derivative, we want to use that rate of change language to speak about it. Okay, so now we just look at each one individually and we say, what is the structure? G, so g of x, what is the structure? 1, 2, 3, or 4? 3. So we're ready to apply the rule. The rule for number 3 says, if we have a function x to the n, and x to the n minus 1. Piece of cake, right? You're going to do that a million times. Okay, overall structure of h. 1, 2, 3, or 4? 3. Agree? Overall structure. 2 and 3. But there's only one structure to it. Is it number 2 or number 3?
I did 3.
It's 2. What is it? It's a constant times some function. That's what the thing is. It's a constant times a function. The overall structure of it is not x to something. The overall structure of it is a constant times something. So we're going to apply rule 2, which says that this is, it's going to be 5. So we'd have to call this, say, a times, we'd have to have a new function. So we'd have to call this 5 times KL, say m. You see? And what is m of x?
x to the fourth.
X to the 4th. What rule does m of x follow?
That's going to be rule number 3.
Yeah, that'd be rule number 3. So we're going to have 5 times, that's applying rule 2, and applying rule 3 would be 4x to the 3rd. Okay? Overall structure. Number 2, so we do the constant times 3x squared. Overall structure of the last one, 1, 2, 3, or 4? 1, right? It's just a constant, and we know that the rate of change of a constant, it's not changing, right? Constants don't change, so that the speed at which it's changing is 0. Okay, and then we could do these. So now, eventually you'll be able to do, even now, you could probably do this all in one step. But it's kind of the point. When things get harder, this is the approach that we want to take to it. What's the overall structure, and how do we see the rules being embedded within the other rules, you see? So this is really number 2 embedded within, number 3 embedded within number 2. But yes, many of you are seeing that you just multiply the 4 times the 5, right? And you get 20x cubed.
So on the homework, you wanted us to do like each step like that, right?
Definitely. And you were writing out sentences to back that up. So, overall structure was sum, but then now we got to do each one individually. We're asking about overall structure of each one. So we had all 3, right? We had one that was this, the first one. 2 were like this, and the last one was like this. Okay, any questions on this problem?
talked about the three notations.
Yeah.
What?
So let's talk about them. So we have, here's the first one we talked about. Rate of change of p with respect to x. Okay, that's actually our average rate of change function, and we know we get it's essentially equal to whatever our rule is for very small h. So this is our average rate of change function, and for very small h, it's essentially equal to the closed form rule, essentially. Okay. Then we have this, the notation we have is shown below. So, what is that right there? It's the rate of change of p with respect to x. Okay, that's what we're going to call it. And the last one is, or you might see it like this. Okay, and what's that? What is it? The rate of change of p with respect to x. The rate of change of p with respect to x. Okay? This one actually kind of displays the meaning a little bit, right? Because what? A very small change in what? Y. A very small change in x, right? So it has that rate of change, delta y over delta x, kind of implied in that notation. So you could argue maybe this is the best one because it's really showing what it is it's calculating, but they're all valid. This one is our average rate of change, and these two are our exact rate of change. But as h gets very, very small, they all are the same. Okay, other questions on that? Okay. So we're going to go on. Let's practice here. Let's talk about open and closed forms. So practice. I want you to write the average rate of change function for x to the n in open form. Right? I want to write it out as the average rate of change. Write that out as the average rate of change. And then, as h gets very small, what does that essentially equal to? So you should be able to do this. Hopefully that's very easy, and hopefully this is we've done it enough times that you know what it is. So let's see who wants to try. Stephanie, how about this one? Not sure. Okay, Sharon. Left. Okay, so for this, we're going to leave it off because we just want the average rate, but yeah, keep going.
Of the function x minus, or x plus h minus f of x divided by h.
Okay, and so what would that be? So that's our, but what would it be for this particular, for x to the n?
X to the n plus x to the n plus h.
Careful. What is f of x plus h? Not x to the n plus h.
X to the n. X plus h.
Lauren.
Is it x plus h to the n?
Okay.
Minus x to the n over h?
Yes, it is. That's what it is. So you're going to say, Connor?
Yes.
Yeah, that's what it is. So if that didn't come quickly, it needs to start coming quickly. That this is, we're using the definition of our average rate of change function, change in y over change in x. Okay, which is our f of x plus h minus f of x over h. Okay, what's this? As h becomes very, very small, that thing is essentially equal to, so you can think of it as had all those, remember we added all those h terms, right? All those terms that had h with it, you could put those on there, and as h gets small, essentially we have that.
So, for this one, because n is representing any number, correct?
That's right.
Okay.
Yep. Okay, so if this is the average rate of change function, how do we get the exact rate of change function from that one? Beth?
Take the limit
Which limit?
of
Limit as h approaches 0. Gives us exact. So the rate of change of x to the n with respect to x is the limit as h approaches 0 of that rate of change function. Okay? And then what's our exact closed form? What's our exact closed form rule for x to the n? I stumped you there. If you have x to the n, what's the closed form rule to get the rate of change function?
Isn't it there already?
Yeah, it's the same thing, right? It's that. So this is saying if you take the average rate of change function with h sufficiently small, yeah, you get the rule, right? You get the rule. So now if we're writing the exact form, we have the rule. Okay, so on the left, open or closed form? Open form on the left. And then close on the right. Okay? Top row, exact or approximate? It's based on average rate of change, right? Based on average rate of change. So it's approximate. We're saying, and this is saying h small. Okay? And then second line? Exact. Okay? Any questions on that? Okay, let's find this. Square root of x is a very common function. It shows up a lot. So we're going to derive the closed form rule. What will be the first step in deriving the closed form rule? So first of all, we'll need, along the way, we're going to need this principle from algebra, that a minus b plus a plus b is a squared minus b squared. So we'll keep that on the side as a tool that we're going to need eventually. If we want to find what the closed form rate of change function is for square root of x, where do we begin? Everyone should be able to write it down. So where would you begin finding the rate of change, the closed form rate of change? You begin with what? So everyone should be able to write this down. We're going to don't use exponents. We're going to leave square roots the whole way. We're going to leave in square roots the whole way. Don't change to an exponent. I'm not asking you to change to an exponent. I'm saying what is the first step in finding the closed form rate of change function for that? What would the first step be?
Think of f of x equals x plus h minus x over h. Or is it f of x plus h?
Marcus? Yeah. Yeah.
The square root of x plus h minus the square root of x over h.
He wants the square root of x plus h minus square root of x over h. That's it. We write out our open form of the rate of change function. So if you're going to try to derive or come up with a closed form rule for a certain function, then you need to start with the rate of change of the function, and we can write down what that rate of change function is. Okay, so here's where this comes in. So what we want to do is, since we have square roots, if we had those squared, then the square roots would go away, right? And that'd be nice. So what do I need to multiply the top by to make those squares, to use this principle and make those squares go away? So what do I have? I have one of these. Which do I have? I have the minus, and I want the plus, right? But if I do that to the numerator, I have to do it to the denominator to not change the value, right? So I'm really multiplying by 1. And we did this because now it's going to simplify our numerator, right? We're going to use the a squared piece b squared, and the square roots go away. we get x plus h minus x. So that's essentially a squared, and that's b squared. Okay, numerator becomes h. H over h becomes 1. And as h gets small, this thing is essentially equal to 1 over square root of x plus square root of x, which is just 2 of those. So 1 over 2 square root of x.
Wait,
Where did I lose you, Corey?
after x plus h minus x.
Leaves h in the numerator. H over h is 1.
Okay, so you took out an h.
And so this is 2 steps.
Okay, that's what.
No, I didn't take out an h. The h was out already here, and that just equals h. X minus x is 0. Just left with h. What's that? Yeah, I'm just explaining that. You see it?
So,
Are you looking at the numerator or the denominator?
the numerator.
It's just what's x plus h minus x.
Okay.
X minus x is 0. You just left with h.
Okay.
You just have h in the numerator.
It's weird where like the h over h is like pulled out and the one up here.
It's kind of like a little bit 2 steps at once. Yeah, the whole numerator is just h, right? The whole numerator is just h. Then we want to combine it with this h, so it goes away. And then from here to here, we're saying what? H is essentially equal to this when h is very, very small. Okay, so we got our closed form rule for square root of x. So now I want to show you something. Now some of you have the intuition to do exponents, so let's do that now quickly. So what exponent is square root of x? So based on what we've done so far, what does that kind of look like?
X to the n.
Yeah, so it's kind of like, well, it's x to the n, but we got a fraction there. So let's give it a shot. What would it be? 1/2.
X to the negative.
And it tells us we know that we want to do n minus 1. 1/2 minus 1 is? Negative 1/2. So what's a negative exponent mean? And what is 1/2 exponent? Look at that. It worked. What's that?
That way is so much
It's different. It's totally different. Because this is not proving the rule. This doesn't prove what this is. The first time we did it, we were showing where that came from. Now I'm just verifying that x to the n, the closed form rule, works for fractional exponents. So you can't compare it. It's like apples and oranges. Okay. Okay. So, in fact, the x to the n rule works for any power of x except 0, because x to the 0 is 1. So let's just practice here. Let's do a couple. So, use what we call the power rule. So, this is the power rule, okay? This is the power rule. So use the power rule to find the rate of change functions for these 3. So it takes you just a minute to crank these out. The last one, if you're going to use the power rule, what do you need to do first?
Change it to a power.
Get the power, right? So get it to look like x to the something. If you're going to use the power rule, you got to get it to look like x to the something. Megan, did you get x to the 16.3?
I got 16.3 x raised to 15.
Here's what she's offered up. Agree? Yeah. You literally follow the rule, whether it's a decimal, a negative, or a fraction. You just literally follow it. That the old exponent becomes the coefficient, and you just, no matter what you had before, you subtract 1. Okay. Richard, get x to the minus 8. Negative 8. Negative 9 or negative 7? Go with your gut. You literally subtract 1. Negative 8 minus 1 is negative 9. So you're right.
But then wouldn't that be negative 8 over?
If you want to rewrite it, you could rewrite it as negative 8 over what? If you wanted to. Yeah, either one. Both the same. So notice that if you start by rewriting this one as 1 over x to the 8th, the rate of change function is not what? 1 over 8x to the 7th. You see? That is not the same as our true rate of change function. So if you can use the power rule, get it to look like this. You can't just use the power rule if it's in the denominator. Okay? Do you see that? You just can't use it because that's the same as that, but that's not its rate of change function. This is its rate of change function. Make sense? Yeah, so always get it to be x to the something, whether that's a fraction or a negative or whatever. Okay, this last one, we said we first want to rewrite it as a power. So what power is that? 3/4 or 4/3? 3/4. Okay. Olivia, can you do this one? Rate of change of x to the 3/4?
Would it be
3/4 x
to the 0.25?
Okay, so what we can just do it in 2 steps. We want 3/4 what? Minus 1. So we just got to make sure we got that right. What is 3/4 minus 1? Negative 1/4 instead of negative 0.25. And then you could change that, if you want to change that back into a radical form, you can. It'd be 3 over 4. 3 over 4 times the 4th root of x. 3 over 4, 4th root of x. Questions on those? Okay, so the moral of the story is the power rule works on any power. It works on negatives, it works on fractions, decimals, and you literally follow the rule. You literally, no matter what that original power was, you literally just subtract 1. Okay? And then we kind of got there by deriving this rule, that the rate of change function for square root of x is 1 over 2 square root of x. This is one that comes up a lot. Questions? Okay. How about this? Same or different than our power rule?
Different.
So what is different about this? Stanley?
Now our input is the power rather than our input being raised to the power.
Well said. So the input is now the exponent. So before, the input was the base. And this was some number. Now the input's the base. But nonetheless, students throughout the ages have tried to make the rate of change what? X times b to the, okay? It's not even close. Because this is a totally different kind of function, right? This is what's called a monomial, right? A monomial. What kind of function is b to the x? What kind of growth is that? Some are saying exponential function. Okay, so a monomial and an exponential function are totally different types of covariation. Totally different types of relationships. So here's your warning. Don't do that. Don't do that. Okay, So let's, if we want to derive the closed form, how will we start if we want to figure out what the closed form rate of change function is for b to the x? How do we start? Everyone, so now everyone should be able to do it. Everyone. Closed form. So our goal is the closed form rule for the rate of change function of b to the x. What would our first step be in finding out that rule? Okay, everyone is going to do it for themselves. What will it be? Everyone gets this. David, can you do it?
B raised to the x plus delta x.
B raised to the x plus. And what are we calling that nowadays? Yep. Okay.
Minus b to the x.
Here's what's been offered up. How many people wrote that down before I did? Okay, needs to be more. Okay, needs to be more. We got to get the hang of this. So we can always start with what's called the definition, our definition of the rate of change, the average rate of change function, right? That's where it all started. Finding rate from accumulation all started with an average rate of change function, the change in y over the change in x. Okay, so we need to now it's algebra time. We need to do some work on this to get something that is useful. So really the only thing we can work on is this. What does that equal based on our laws of exponents? Yeah, when do you add exponents? When you have the same base and you're multiplying. That's when you add. So we're going backwards on that rule. So when you have the same base and you're multiplying things like this, we know that you can just add exponents. Why? Because this is x b's multiplied together and then h more b's multiplied together. So how many total b's multiplied together? X plus h. If you get x b's and then h more b's, then you got x plus h total b's. Okay? All right, what can we do now? Can't get rid of anything, but we can factor out. So here's where we want to look at this and think about ideas here, ideas. So what are we finding? We're finding the rate of change function for b to the x. So what are we seeing that it involves? It involves, what is that? It's not a constant multiple because it's, but where, yeah, exactly. So this, in the case of an exponential function, the rate function involves the original function. Okay, that's the first thing we see there. That the rate of change function is involving the original function. Okay, so now we got to make heads or tails of this. So what happens as h gets very small? This turns into 1. So I'll rewrite it here. So this goes to 1. So the whole numerator goes to 0. And so the whole thing goes to not 0. 0 over 0. Okay? Now, 0 over 0 has 3 possibilities. This is called the indeterminate form. And it's not, why? Because it's unknown what it is. It depends on the situation. It could be 0. It could be some value. Or it could go to infinity. So it could be 0, it could be some other constant value, or it could go to infinity. Those are the three possibilities whenever you get the situation of 0 over 0. So let's see if we can whittle it down. What are we doing? We're building the rate of change function. What if it was case number 1? If it was case number 1, what would our rate of change function be? The whole thing would just be 0, right? Make sense? We got an exponential function. Its rate of change is 0 everywhere. No, exponential functions, they have a changing rate. They have a changing rate, right? So if it's an exponential growth, that rate of change is increasing. It's not 0 everywhere, okay?
So what happened to the b of x though? The b to the x?
We're just,
Is
well, we know it's the original function. Now we're just analyzing what this is.
Why is it no longer divided by h? Am I just being stupid algebraically? Like when you pulled it out of the function, why is it no longer divided by h?
The b of x?
Yeah.
Then it'd be h squared in the denominator. You want b of x over h? Then you'd have h times h. You only got one h.
But when you pull it out, shouldn't it stay?
What's that?
Factor it back in.
If you want to put b of x over h and this over h, you really have, then that's really h squared in the denominator.
I see.
We just have one h. So I'm going to group it with this rather than this.
Just like if you were multiplying right now, it just
Okay.
it's like 5.
Are we good?
Mhm.
Make sense? Okay.
But
So
isn't
we're,
it still part of the function though? 'Cause-
yeah, this isn't the function. I'm just analyzing this.
Oh,
We're just analyzing to see, because this is what's going to change as h gets very small. As h gets very small, we're just going to have the original function there, and then we're going to have this thing's going to actually change, so I'm just analyzing that part of it. We're going to come back to the whole thing in a second. So we're saying this part of the parentheses, as h gets small, since it's 0 over 0, has three possibilities. Is 0 a viable option? No, because it would make the rate of change function 0. Okay, how about infinity?
No.
Viable option.
No.
Why not? No, so to talk about what would the rate of change function be then if it was... Yeah, so the rate of change itself would be an infinite rate of change everywhere. And that's certainly not an exponential function. Has some rate of change profile, right? It's not just... the quantity isn't just changing infinitely fast for no change in x. That's what that would be saying. The quantity would just be changing infinitely for literally no change in x, always. Doesn't make sense. So we're left with... So this thing, what makes sense is, this thing is some constant. So what's the idea behind the rate of change of an exponential function? The idea behind the rate of change of an exponential function is, we couldn't articulate it. Dan. If we have an exponential function, our hypothesis is, what about its rate of change function?
I'm not sure.
Tyler.
That the rate of change function will be the original function multiplied by some factor.
Yeah. Yeah, so the rate of change function will just be some constant multiple of the original function. That's going to be our hypothesis, based on the math that we did here. Make sense? So let's test it and see what happens. Okay, so here I've got the original function, and I've set b to, I got a small h, I've set b to 7.5. So we're going to start by looking at 7.5 to the x. Okay, I'm going to graph that. There it is. Okay, and then I can, so I've set up the rate of change function, and I've got a very small value of h. I've graphed it, so I can slide x along here and look at different values of x. So I'm going to graph the rate of change function, and our thinking is that the rate of change function will be, what's our hypothesis? Some constant multiple of the original. So is it? So let's look at x equals 0. What do you think at x equals 0? So this is the original is blue, rate of change is red. What's that?
It's about twice as much.
It looks like about twice as much. So what would your hypothesis be for the rate of change of 7.5 to the x? So the rate of change of 7.5 to the x, we're asking, is it what? 2 times 7.5 to the x. So if that's true, then how could we check it? We got the graph. So you're making your hypothesis based on x equals 0. So how can we verify that? But we don't have the rate of change function. See, we can't plug in 0 because we don't have it. We have this. We have the
Put 0 into the function
put 0 into the function to get 1. There it is.
times 2 is 2.
No, so we want to look at other values of x, right, and see if it still works. So here I'm going to put x is 0.3. If this particular is right, then what should the rate of change function be? So at 0.3, y is 1.8 in the original function. So this should be about 3.6, and it is. Okay, I'm looking up here. Looking up here. So here at 0.3, the original function is 1.8. Rate of change 3.6. Seems to work. So let's do one more. How about back here at, oops, let's just do one back here. Negative 0.3. At negative 0.3, the original function is 0.54. Or sorry, 0.55. So we would expect 1.1. There it is, 1.1. Okay, so in this particular example, it seems to be working. All right, what about b is 4? So now I got 4 to the x. So how could we find this constant using the graphs? How could we find what that constant multiple is for this particular function 4 to the x using the graphs?
Take a value on each of the graphs.
Okay.
Find out what the multiple of one to the other is.
So tell me exactly what to do.
Go to x equals 0.
X equals 0.
Find the value of the red graph.
Value of the red graph. Sorry. 1.38, was it? 1.38639. Okay? And?
And then obviously, I mean, you can double check it, but it looks like the blue graph is on 1.
So if x is 0,
That means that,
is it 1?
yeah.
Sure. So what do we think this one is? So r,
So then it's whatever that value was, 1.38629.
1.3864 times 4 to the x.
63.
I rounded 639. So I rounded to 64. How could we find that constant with another value of x? Suppose we didn't use x equals 0. So suppose I go out here to 0.9. How could I find that value at 0.9? Not the same thing. What we did there is we just took the y value at the rate of change. So here it's,
Oh no.
what do you want to do?
Subtract.
Subtract. Subtract this one and this one. y2 minus y1 is going to give us that constant. Zoo, what do you think? I want to get this constant right here. How could I do that at x equals 0.9? Okay, what's that? Would be divided by, right? The multiplier to get from this y value to this y value would be the ratio. Wouldn't it be the ratio? Okay, so that's what I got right here. I set up the ratio of the rate to the original function. If I move x, what should happen to that ratio? It's going to change? All right, I'm keeping b 4. b is 4. So what about that ratio of the function, the rate, to the original function? If our hypothesis is true, that should stay the same. Watch, ready? Doesn't matter what x value you pick, the ratio of those, or this constant multiplier, stays the same. So it's very much seeming like our hypothesis is true. Okay, so now I'm going to make b, say 1.5. What just happened?
Got much more.
How does the rate compare to the original function now?
Pretty close.
Different than the other ones. The rate is, it's underneath. Now it's a fraction of it, right? But still, that constant multiple idea still works. So for b of 1.8, it's still a constant multiple, 0.587. So this begs a question. So watch as I change b. This begs a question. So here, the rate of change is 1.8 times 1.48, 1.3, 0.74, 0.47 of the original function. So what is of interest here?
What if they,
Corey, what's that?
what are they the same?
Yeah. So look, do you see that there's for some value of b, the rate of change function is equal to, that constant multiplier is 1. So it looks like it's around 2.7. So let's 2.6. Let's zoom in our x values here. Oh no, that's not what I want. Okay, what I wanted was this one. So I want it zoom in. So 2.6 to 2.8. So we can fine tune this. So somewhere around a b value of 2.7, the rate of change function is 1 times the original function, or in other words, it's the same function. So where is that? There we go. So this is a very special function, 2.718 to the x. Why is it very, very, very special? What's that?
It's its own derivative.
Okay.
I'm sorry, it's its own rate of change.
Yeah, so the function itself is, its rate of change function is the original function itself. We have a constant, our constant multiple for this particular base is 1. And this is an infinite, non-repeating decimal like, what's another one you know like that? Pi. This just goes on and on and on and on. 4590. Okay, so just like pi, and it goes on and on and on and on.
Is that really what it is?
That's really what it is.
Yeah,
I have a little trick. So come to my office, I'll tell you later. All right. Okay, so it's a number like pi. It's a very special number because it's the base for the exponential function that has its rate of change function is the same. So if we plug in an x value, the quantity at any x value and the rate at which that quantity is changing is always the same. Really important function. Okay, and so many of you have said, you know what this number is. What we call pi, we call this one e. So when you see e, it's called the natural base. It's the base that returns the same rate of change function as the original function. Okay, so back to finishing up here. So we said that if you have b to the x, its rate of change function is just some constant times the original function. So we verified that by sliding x and seeing that that ratio didn't change. It's a constant multiple. Okay? So this base is the value of b for which that constant is 1. In other words, its rate of change function is the same as its original function. But you can use e to the x. Thankfully. And actually, this is an approximation of that number. No matter how many decimal places you take, it'll always be an approximation. E stands for that exact value. All the decimal places to infinity. Okay? What does that say? So, Jacob, can you read that for me?
Small changes over small changes in x times e into x.
Okay? Talia?
Isn't it the rate of change of e to the x with respect to x is e to the x?
The rate of change of e to the x with respect to x is e to the x. So, here's what we got. Here are the new ones we learned, and we also got just any exponential function we got was bx. What's the rate of change function? The rate of change of b of x with respect to x is? K b to the x. We didn't have time to show was this k is the natural log of b.
Yes, I remember it.
We didn't have time to show that. So we got two new rules. We got the average or the rate of change for square root of x and the rate of change for b to the x. And a very, very special case of that second one, where that k value is 1 and the rate of change function is the original function. Okay, so we're going to stick around, and we ready? Stick around, just do the quiz now. Any questions before you have your quiz? And then you're free this afternoon. Have a wonderful break. There will be homework over break. It won't be posted right away today. I don't think any of you are going to go jumping doing it today. Is that right? So I'll get it up as soon as I can. As soon as I can.
Hey guys, hold on. Finish up taking your notes, and then everything off your tables except for pen, pencil, eraser, and calculator. You probably won't need your calculator, but. And then I'll be passing back homework as well to make sure everything is off your tables. But I see a couple of you finishing up notes, so I'll start passing out when everything's clear, please.
Judy's ready to go.
I know, we're all excited. I'm waiting for everything to be cleared off tables, please.
Cracking the whip.
Still waiting. I see papers. I see people talking.